Okay, Katja, thank you very much for the invitation. It's been a great pleasure to be at this seminar. You know, it's been very great and very interesting talks for the past couple of years. Okay, so today I'm going to talk about a recent project with Plamen Stefanov, who is unfortunately teaching right now and he can't be here. This sort of work is motivated by geophysics, where one is interested in understanding behavior of seismic waves in the interior of the Earth. So, you know, we know that in the interior of the Earth, we have several layers, some of which are solid, such as the mantle or the inner core, whereas we have some layers which are liquid, for example, the oceans, of course, or the outer core. And seismic waves behave in different ways in solid and in liquid media. So for instance, in solids, we have waves which decompose into transversal and compressional waves, whereas in a liquid, we only have compressional ones, for example. So we see this cartoon here that's, has an illustration of what the waves would look, for instance, in the outer core, which is fluid. So what we want to do is we try to understand how those waves behave when they meet the interface between a solid and a fluid. Okay, so as a little overview of what we're going to discuss, so we're going to start with the model that we used, which apparently is not completely clear because everybody's using something different. We are going to discuss the well-posedness of the system of partial differential equations that we set up. And then with the main part that I'm going to discuss is the microlocal transmission problem. And at the end, I will say a little bit about an inverse problem, which is sort of like an application of what was there before. Okay, so starting with the model. So let's start with our assumptions for our solid. So we're going to assume that we have an isotropic linear elastic solid. So we're within the realm of linear elasticity. Let's start without making any reference to how a solid will interact with a liquid. Just look at U, which is an open set, and we have our isotropic elastic solid occupying it. And let's assume that we have a Riemannian metric on U, which is going to function mostly as a device to change coordinates later. If you prefer, you can think of it as Euclidean metric. Now, the main quantity that we're going to try to model is going to be the particle displacement. And there are different ways you can do that. I mean, you can think of it as a vector field or as a covector field. In this work, we're thinking of it as a vector field. And then it follows by Newton's law that the displacement satisfies the elastic wave equation. So here, rho is the density of the solid, and we have the second time derivative of the evolution of the displacement being equal to the elastic wave operator applied to the vector field U. Here, this elastic wave operator is given by the divergence of the Cauchy stress tensor, which is given by the expression here. So we have the Lamé parameters, which we do not assume that they're constant. So we assume that they are smooth and they're positive. And the Cauchy stress tensor is given by the bulk modulus or incompressibility modulus times the divergence, and we assume that we have a metric divergence here with respect to G, times G inverse, plus 2 times the shear modulus times the Cauchy strain. Now, the strain is the familiar from tensor tomography symmetric differential, except in tensor tomography, we usually think of the symmetric differential as the covector field. Here it's of a vector field. In coordinates, it takes this familiar expression over here, except usually in tensor tomography you would have lower indices for your symmetric differential. Here we have upper indices because we are thinking of it as a vector field. Okay, so this is the expression for our elastic wave operator, and should remark here that this is actually an elliptic operator. So it's an elliptic operator acting on the vector field U. This is going to come up a bit later. Okay, so this is our setting in the solid, and so it is well known in the geophysics world that if the metric is Euclidean and you have constant Lamé parameters and constant density, then you can actually decompose your waves into shear and pressure waves. So you can write waves as the curl of a vector potential. So this is a vector, it's a vector field. And you can write the P waves as the gradient of a scalar potential, where those potentials satisfy here a principally scalar hyperbolic equation, and here we get the usual sort of wave equation with speeds CS and CP, where those speeds are here. So they are given by the ratio of certain ratios, between the Lamé parameters and the densities. And an important observation here is that, if the Lamé parameters are all positive, we have that the P speed is always greater than the S speed. So here we have the compressional waves in this very beautiful illustration where the particles oscillate in the direction of propagation, whereas the S waves or shear waves, the oscillation is in direction which is perpendicular to the direction of propagation. Okay, so this is our setting for the solid. So this sort of tells us what to expect. So it tells us to expect that in a solid we should have this decomposition of waves into sort of polarizations. Now, in the non-constant coefficient case, we're not going to have exactly this sort of decomposition, but we're going to see that we can have it microlocally. So now let's see what happens with the fluid. So there is quite some variety in the models that people use here. The one we decided to use is, we found it in sort of geophysics literature, where we model the velocity and the acoustic pressure. So people are not as much interested in the displacement as a quantity that one tries to understand in a fluid. So we have the velocity and we have the pressure. And here the density of the fluid appears, which again, we assume that is smooth, positive, but not constant. And we have the bulk modulus over here, which measures the resistance of the fluid to compression. Now, it is not too hard to see that this system actually can be decoupled into two equations. Here we have the usual acoustic equation for the pressure. This is pretty well known. And V also satisfies an equation that looks like a hyperbolic equation, except here we have an operator which is not elliptic. So the divergence kills basically any potential vector fields. It kills any curls. Okay, and from here we can see that we only have compressional body waves in the fluid, so we don't have those shear waves which in which particles oscillate in direction perpendicular to the direction of propagation, and the wave speed is given by this quantity here. It's the ratio of lambda over rho in a square root. Okay, so this is our setting in one and in the other medium, and now let's see how the two actually combine together, because we said that we're interested in understanding what's going on at the interface between the two. So we have to see how they interact. Okay, so the geometric setup we're going to use is fairly simplified. So, if you want to be more accurate and try to model the Earth more accurately, you could take several layers, some of which are solid and some of which are liquid. Here we're just taking one solid, which is enclosing a fluid. And we assume that the boundaries here, so the interface gamma and the boundary, are smooth. So the way we're using the simplified, the reason that we're using this simplified setup is just to make the exposition a little bit more clear. It's not that the problem becomes easier to solve or anything like that. Just for a matter of presentation. Anyway, most of what we're going to do is going to be local anyway. So we're going to be looking locally near the interface. Okay, so now, as we said, we're going to have our solid, in which here we are doing this usual thing of breaking the hyperbolic equation for the displacement into a first order system. And in our fluid, so this is the solid case, and in the fluid, we are going to have the equations we mentioned just before. Then we need some transmission conditions, which is where the transmission problem actually takes his name from. So the first condition is a kinematic condition, which says that the normal component of the velocities has to be continuous. So we don't have one of the bodies somehow getting inserted inside the other, but we are allowing tangential slipping, so the two layers can slip against each other. That's fine. Moreover, we need a dynamic condition, which tells us that the traction across the interface between the two media is normal to the interface. This nu is the unit normal. And it is actually continuous. So the normal component is continuous. The tangential components of the traction vanish. So this n of u, we should be thinking of as a Neumann type condition. And so this is behaves sort of like a normal derivative for all intents and purposes. On the other hand, on the outer boundary, we are going to consider a dynamic condition as well, which says that the traction should vanish. So this is in contact with, say, air or vacuum. And we are going to have some prescribed Cauchy data. We're going to see in a moment what we need about those. And we are going to also need a technical assumption, which I'm just mentioning it here, but I will not say too much about where it appears. It's just a compatibility condition to be able to solve some sort of Neumann problem. Okay, so this is our model. This is our main model. So it wasn't exactly clear, what is a correct model to use. I mean, many different authors use very different models. So some people that are actually using pretty much the same are mentioned here, even though we were actually not aware of their work until quite later. But I'm also mentioning a few other works that are from the math literature, let's say, well, except those who are geophysicists. But there are people who use time-independent models as in stationary, or some people consider viscosity in the fluid, which we're not doing. Or there is, for example, this work where they're considering gravitation and earth rotational forces, which we're also not doing. Okay, so before we actually do anything, before we start studying the problem microlocally, we would first make sure that we have well-posedness, so that our equation actually has a solution. So for that, what we actually did is that we considered an equivalent system for the displacement in the two media. So initially we had velocity and pressure in the fluid, but now we write it as a system for displacement. And, we have the elastic wave equation here that we saw before. So second derivative in T is the elastic wave operator here. And we have a second order PDE in the fluid, where now this operator here is not elliptic. So it's gradient of the divergence, roughly speaking. And that's not an elliptic operator, and that creates a lot of trouble. So here the transmission conditions are pretty much what would naturally follow from the ones we saw before. Okay, so what we did is, we considered those two operators here, and we, oops, this is kind of weird. Yeah, okay. We gave them the name P plus and P minus. We consider it as an unbounded operator on L2 cross L2, acting on smooth functions satisfying transmission conditions. And one can check that with those transmission conditions satisfied, we actually obtain that this operator acting on pairs of functions is symmetric and is positive. So that tells us that there exists a self-adjoint extension, and therefore we can use, the usual sort of propagators to actually show that there exists a solution. So for well-posedness, up to this point, you're pretty much fine, but we wanted to understand exactly what the domain of this operator looks like, and took the extra trouble of identifying it. So we were not aware of somebody exactly doing that before, like exactly identifying this domain. And it actually took quite some effort to prove that this is actually the case. And if there is a reference, I'd be happy to know. And here it turns out that the self-adjoint domain of this operator is H2 regularity in the solid, and it is this space in the fluid, which is L2 with H1 divergence, and with transmission conditions, which one can check that they actually make sense for the space that we have, for this regularity that we have in the interior. Okay, so this tells us what the space is in which we actually have well-posedness, which brings us to our first result, that the original system, translating back to the original system, we have a space in which we actually have nice solutions. And in fact, we also have constant energy. So this is a nice self-adjoint problem with preservation of energy. Well-posedness has been shown for similar systems. I don't think that, at least from the literature that I'm aware of, somebody has used exactly this method. So I don't think, for example, that the domain has been identified, and that has been actually quite important at a later stage. Okay, so now we're happy in the sense that we know that we have solutions and they're unique and everything, as long as we have reasonable regularity, we have our transmission conditions be satisfied for our initial data, and we have this technical assumption that we saw earlier. And now let's get into the sort of the main topic, which is the microlocal treatment of the transmission problem. So really, which is sort of the main point of this project. So what do we want to do? We want to construct a solution for this system up to smooth error. So we want to construct the parametrics for which the propagation of singularities is clear and is easy to understand. So at least as far as I am aware, there hasn't been too much attention on this problem from a microlocal point of view. So some very related works are listed here. So there is a sort of old paper by Yamamoto, and there is this paper by Stefano Fullman and Vashi, which is sort of one of the main inspirations for this project. And so those deal with transmission problem microlocally between solids layers. So you have two solids being in liquid contact, and you investigate microlocally the behavior of this system. And there is a recent work also by Zonke Hansen from 2021, which is still working with two solids, but also is allowing for the possibility of anisotropic solids, which is pretty interesting. Those works, as far as I remember, deal with the isotropic case. But at least to our knowledge, this hasn't been studied for the solid fluid case. Okay, so to sort of give an idea of what we are after and what kind of solution we're trying to find, let's start with a simple example. So let's start with an acoustic equation with Cauchy data. So here this acoustic equation is written in sort of divergence form, and the corresponding wave speed is the square root of lambda over rho. And we have some Cauchy data, and it is very well known and classical. It goes back, I don't know, probably at least 60 years or so, that one can construct solutions for such a problem using geometric optics. So you can, at least locally a priori, you can construct a solution by solving an econal equation to obtain a phase and put it inside an oscillatory integral, where the amplitudes are subsequently going to be solving transport equations. So here, this solution is going to be equal to the Cauchy data, for instance, when t equals 0. So this is, we have Cauchy data at our space-like hypersurface, and we're trying to construct an asymptotic. We try to construct a solution up to smoothing operators for the Cauchy problem. So here, yeah, actually, I'm going to say that in the next slide. But yeah, so the point is that in order to be able to solve this problem, you want to be able to solve this econal equation. And once you have that, you are able to produce the amplitudes by solving transport equations along the null-by characteristics. And of course, those are no local expressions, but you can patch them together. They're FIOs, you can compose them, and you can make sense of them as global objects. And the beauty of that is, so to speak, that those are oscillatory integrals for which the behavior of singularities is clear. I mean, you can read it off the oscillatory integral. I mean, this looks kind of messy, but the point is that you can understand exactly what the singularities look like. So this gives you a very good picture of how singularities propagate. Okay, so this is the kind of thing we're looking for. Though now we are interested specifically in the situation where we're near a time-like hypersurface. And here time-like is, terminology that comes from relativity, but the point is we're looking at, a hypersurface of this form sitting inside, M cross R. So we have our, if you want to think about it with time being vertical, so we have, so to speak, the gamma being here, and then this is the time direction, and we want to see what happens at the interface over here. So for the rest of the talk, and actually that's also what we're doing in the paper, we're focusing on the interface between the solid and the fluid. I mean, one should also consider the case of the hard boundary on the outside, but we don't examine this in detail because it is treated in detail in the Stefano Fulman-Vasci paper that I mentioned earlier. So we're just going to look at what happens near the interface between the solid and the fluid. Okay, and now we want to show microlocal well-posedness, which means that we want to show that we can construct those approximate solutions up to smooth error by constructing parametrices separately on the two sides, so in the solid and in the fluid, and showing that we can actually match those together via the transmission conditions to obtain a parametrics for the full system. And the theorem is actually that you can do that, at least in all of the cases that we examined. I'm going to put the theorem at the end as a sort of summary, and I will try to explain sort of how the logic goes in showing that. Okay, so now, let's see, this is, oh, here we go. Okay, so first we would like to reduce the study of the fluid to a study of a potential. So what you can do is you can have some sort of Helmholtz decomposition for the velocity, for actually the momentum density, this product of density and velocity in the fluid, in a divergence-free part and a potential part. And to obtain this decomposition, I mean, usually you have to solve a Dirichlet problem. In this case, you have to solve a Neumann problem. So, there is actually, you can get this psi up to a constant. But you can turn the original system into an essentially equivalent system, which has the elastic equation here in the solid. And in the fluid, we have an acoustic equation with a source. And we have some natural transmission conditions. And we have certain initial data. It's a Cauchy data. Now, this source here, I mean, it could be problematic in principle, but it is actually constant in time, turns out. So if you assume that your initial data is smooth near the interface with the solid, then the source is never going to actually get near the solid. And that's what we're going to assume in what follows. So we are going to assume that the initial data for the system were smooth near the interface and the boundary. And now we want to do the following. We want, as we said before, we want to construct parametrics near the Timelike hypersurface in the fluid. So we're going to seek approximate outgoing solutions, where this means that they propagate singularities only into the future in the fluid, not into the past. And we want them to have certain Dirichlet data. So we want to construct an outgoing solution with certain Dirichlet data, and then we're going to see how this Dirichlet data can match from the other side. Now, the form of the solution is going to depend on where the wavefront set of F lies. So there are some possibilities for that, and here is where actually the presence of a metric becomes very useful, because it tells us that we can basically choose nice coordinates near a point that we're interested in. So we're going to study the problem locally, and we can choose nice coordinates, at the point we are interested in. We can take them to be Euclidean, take the metric to be Euclidean, and we can sort of solve the problem invariantly, to put it this way. So in that case, we can deal with a curved hypersurface, without having to actually do very heavyweight computations. That's, of course, as far as you don't have to go into looking at objects that depend on derivatives of the metric, which would be a different story. But as long as you're looking only at objects that depend on the values of the metric, then you're fine. Okay, I should say that this idea was exploited already in the Stefano Fulminbashi paper, so that's where this came from. Okay, so now we want to construct those outgoing solutions, and there are three possible cases for where the wavefront set of F can lie, and based on where it is, we have a completely different behavior. So there are three possibilities. One is the hyperbolic region, one is the elliptic, and one is the glancing region, which sort of depends on the location of a covector. So here, this is the hypersurface, with here having sort of the tau variable, and here this is the C prime variable on gamma cross R. And here, hyperbolic region is over here, and elliptic region is over here, and glancing is at this light cone on the Timelike hypersurface. So we're not going to look at constructing a parametrics near if the wavefront set is in the glancing region. So this is a much more delicate case. It has been studied by some authors. I think it was Melrose and Shostrand, or Melrose Taylor, and I don't remember which one of the two. And by Stefano van Podov, who have constructed some parametrices for, in the case of the glancing region, but we're not going to look at that. Okay, and we are going to now look first at the hyperbolic case, and assume that the wavefront set of the Dirichlet data is there, and see what we get. Well, it turns out that you can construct a parametrics with geometric optics in much similar way like the one we saw before for the problem with Cauchy data. So here we need to solve an econal equation, right? So this is always a a standard theme, let's say, in this geometric optics business. So you want to be able to solve the econal equation with the initial data over here, and if you're able to do that, then you can solve for the amplitude by solving transport equations along the null bicharacteristics of the Hamiltonian corresponding to the wave speed of the fluid. No, I should say, so here you can notice what happens when we are at the hypersurface, at the Timelike hypersurface, which is given by x3 is equal to 0. So notice by this asymptotic expression for phi outgoing that this part is going to be 0 when x3 is 0. And here we have this expression to be equal to 1. So basically we get the inverse Fourier transform of f hat, which gives us f. So that gives us the correct Cauchy data, the correct Dirichlet data at the hypersurface. Okay, so this gives us our approximate solution, and then we can actually make sense of a outgoing Dirichlet to Neumann map by taking the normal derivative. So this is the derivative with respect to the unit normal. And this is an operator of order 1 with principal symbol, which is given by this expression. And note that this is elliptic symbol in the hyperbolic region. So up to now, we're looking at trying to construct an outgoing parametrics for the fluid. And if we have wavefront set of the Dirichlet data on the Timelike hypersurface, which is in the hyperbolic region, then we can do that. So we can solve the econal equation. And we can construct the parametrics. On the other hand, in the elliptic case, things become a little bit more complicated because we can't solve this type of econal equation with real values anymore. So what one can do is you can solve it up to infinite order. You have to assume that the imaginary part is actually non-negative in order to make sure that your waves are not going to be exploding exponentially fast as you're leaving the hypersurface. And you can solve the transport equations also, to infinite order. And this type of parametrics that you can construct, so this type of expression, gives rise to what is called an evanescent wave. So this is a wave that actually decays exponentially fast as one leaves the hypersurface. And those waves actually don't propagate singularities inside the body. Okay, so those are the two main cases that we are looking at for the fluid. I should say that also we do get an evanescent Dirichlet to Neumann map in this case, which is a pseudo-differential operator of order 1, which has the a principal symbol which is elliptic in the elliptic region. Okay, now what happens with the elastic equation? Now things are a little bit more involved because we don't have just one, we can't just write it as just one potential as we had before. Remember, we saw before that in the Euclidean case with constant coefficients, we can decompose the waves into compressional and shear waves. And we can find potentials for them. And this is very well known in the geophysical literature. So those the shear and the pressure waves are going to propagate singularities along null-by characteristics of those two different Hamiltonians, where we have the p speed here, and here we have the s speed. Where, as we mentioned earlier, the p speed is always larger than the s speed. Okay, so this is some terminology about the characteristic varieties that they define, but the sort of important proposition here that, so here this formulation comes from the Stefano Fullman and Vaschi paper, but it has been known at least as back as 1975 in one of Michael Taylor's papers. Okay, there is a lot here, but mainly the idea is that one can decompose the wave microlocally. So you can decompose the elastic wave equation and obtain the shear part as the curl plus lower order operator of a potential, and you can get the pressure part as a gradient plus lower order operator. And those, the QS and the QP, so those potentials, they satisfy principally scalar systems. So here the potential, so those equations should be interpreted as systems, but actually the second one is for a scalar, but here we have actually truly a system, but it is principally scalar. Okay, so we do have a decomposition, at least microlocally, to leading order, which is what we care about for the purpose of understanding singularities. And as before, we can seek outgoing solutions up to smooth error near our point in the solid region with given Dirichlet data. I should say that the same thing that you can do with outgoing solutions symmetrically, you can do for incoming. And here this coloring is indicating what would change. So what's the difference from passing from the outgoing into the incoming one? Oops. Okay. So the point here is that one can actually construct parametrices using geometric optics for those potentials. The great part here is that those potentials satisfy principally scalar equations, as we mentioned. Principally scalar hyperbolic systems. And for those, one can construct parametrics in very much the same way as for the scalar case. And again, the form of the parametrices is going to depend on where the wavefront set of the Dirichlet data lives. So now we're going to have more cases though, because we have the p speed, which is greater than the s speed. So we have actually 5 different cases. So we have hyperbolic, glancing, mixed, and elliptic. And as before, we're not going to look at the glancing regions. We're only going to look at the case where we have hyperbolic, mixed, and elliptic case. Okay, so now what is our goal? So we have, as we said, we have waves on the two sides, and we have to make sure that the Cauchy data is going to match at the interface. And we want to, the question we want to ask ourselves is, for each of the 6 possible regions, excluding all the glancing ones, if we can uniquely determine the Dirichlet data of the outgoing waves from the Dirichlet data of the incoming ones, because we saw that once, if we have the Dirichlet data, then we can construct the outgoing waves. Okay, so we basically you have to look at a large number of cases. So you have to look at 6 cases separately. So I don't have time to talk about all of them in detail. I'll just outline the hyperbolic case. So here we assume that we have wavefront set, which is in the hyperbolic case in the hyperbolic region for basically all speeds. So for the p speed, the s speed, and the fluid speed. And we recall that we have transmission conditions. So here, as we mentioned, this is the traction at the interface, which is sort of like a Neumann condition. And we are going to write the wave in the solid. So this is in the solid as a sum of an incoming and an outgoing wave. And we're going to do the same thing for the potential in the fluid. And all we need to do is we need to be able to determine uniquely the data for psi out. Actually, this is not correct. For psi out and for u out, based on those for u in and for psi in. Yeah, this sentence is incorrect. I will fix it. Okay, so how to do that? Well, as we said, for the solid region, we're going to actually construct parametrices for the potentials, not for the full system. And in Stefanos and Vashi paper, it is shown that you can actually relate the Dirichlet data of the full solution to the Dirichlet data of the potentials via an elliptic operator of order 1. Which is, it lives on the hypersurface. And similarly for the Neumann operator, where this one is of order 2. And those are the Dirichlet data for the potentials in the solid. Okay, so you take those operators and you substitute into the transmission conditions, and you do the same with the Dirichlet to Neumann maps that we constructed earlier for the fluid. And then what you have to do is you make sure that the outgoing principal amplitudes can be recovered from the incoming principal amplitudes. So here you have a pseudo-differential system which has a symbol which is given by, it's given in terms of the various operators by this expression. It can be shown that this operator is elliptic, and therefore you can recover the outgoing waves. Which shows microlocal well-posedness in this case. In addition, it follows that you can, it doesn't follow from that, you have to do something extra, but it follows that any configuration in the fluid can be produced by a configuration in the solid. So if you want to have a certain wave in the fluid, at least to leading order, you can do that by sending suitable waves from the solid. This is going to be important for the inverse problem. Okay, so I'll just show some pictures now to illustrate what's going on. So here we have our interface over here, and we have the fluid, which is the blue thing below, in which we have the compressional waves that particles propagate in the direction of, oscillate in the direction of propagation. And we have our P waves and we have our S waves here. So actually at the interface, the shear waves, so those that are they oscillate in direction perpendicular to the propagation, those decompose into shear vertical and shear horizontal, where shear vertical, well, shear horizontal means that the oscillation is parallel to the hypersurface. So this is a terminology that comes from geophysics. And for us, it makes sense only at the hypersurface, not further away from it. But actually, a pretty interesting effect here is that the shear horizontal waves are reflected completely by the hypersurface without transmitting anything on the other side. So if you just have a shear horizontal wave and it meets the hypersurface with the fluid, it does not create any evanescent waves on the other side. So this is a pretty interesting effect. So in some sense, this boundary behaves like a hard boundary, like it was in contact with vacuum. So it doesn't see that there is liquid on the other side. It behaves like vacuum, which is in sort of contrast with what you would expect in the elliptic hyperbolic case, in which we're elliptic in the solid, but we are in the hyperbolic region from the fluid side, and then a wave that meets the hypersurface creates an evanescent wave here. So there is a wave which decays exponentially fast away from the hypersurface. Okay, so there are some more cases which I'm not going to talk about because there isn't enough time. Another interesting case is the elliptic. So here we have wavefront set of the Dirichlet data, which is in the elliptic region for both speeds. And in this case, we actually don't have singularities propagating into the body or coming in from the body. So the only possibility is that you can have waves which propagate along the hypersurface. And actually, in this case, you lose ellipticity for the system, and it is possible to have waves which propagate along the hypersurface if you give it, Cauchy data on a certain hypersurface here. So this is a well-known phenomenon in geophysics that waves between a solid and a fluid are always possible. Whereas, by contrast, when you have two solid surfaces which are in contact, the corresponding surface waves, which are called Stoneley waves, are not always possible. So they may or may not exist. Okay, so finally, the theorem, which basically summarizes the logic that I sort of try to outline, is that if we have solutions of the original system, which, as we said, have to satisfy certain Cauchy data that are supported away from the hypersurfaces, and we also assume that the wavefront set of boundary data of any solutions is disjoint from all glancing regions, then the transmission problem is microlocally well posed. So we can actually find a solution for the an approximate solution up to smooth error. And also, if you're willing to consider Cauchy data on the interface, then those Schulte surface waves are possible. Moreover, we actually show that the difference of the parametrics constructed for the system from an exact solution is smoothed down to the hypersurface and to the exterior boundary. So this is actually showing that is not a trivial problem, and it basically involves looking at a system similar to the one we had, where you now have smooth sources instead of having zero transmission conditions. So you have transmission sources which are smooth, and you would like to show that that a solution of this system with those smooth transmission sources is actually smooth. I'm not going to go into detail on how this goes, but I would say that this is a type of problem that people have been studying. It's called transmission problems. There are some very difficult papers that deal with problems like that by Mark Williams from, I don't know, the 70s probably, or 80s. So, I mean, this is quite important because, you construct the parametrics, but then you want to make sure that actually it differs by an actually smooth solution. So this was kind of a sort of technical part of the paper that took about, I don't know, 10 pages of estimates to make sure that this actually works. But it is possible, and it works. Okay, so I'm not going to say much more about how this goes because I'm out of time. Can I have 2 minutes maybe?
Sure, please.
So I'll just say a quick word about the inverse problem. I won't say too much about it. So the question that we included sort of as an application of all the study, which was sort of the main point, is whether we can recover material parameters from the outgoing Neumann to Dirichlet map. So the Neumann to Dirichlet map on the outer boundary. So you have your outer boundary and you have your inner fluid, and you have the Neumann to Dirichlet map with respect to the full system out there. And so one of the issues is that you might run into a situation where in the fluid, you might send some waves in, and then they might get totally reflected forever and never be coming out to give you any information. So that is an issue that you have to somehow assume it out somehow. So there has been quite some work in this type of problem. So there are some works by Rachel from the early 2000s, which were dealing with, if I'm not mistaken, from basically determining the density of an elastic medium. And of course, there are the works by Stefan Ullmann and Vashi, regarding boundary rigidity and so on. And there have also been some recent works by Kadei, De Hoop, Katznelson, and Ullmann, and also a very recent paper by Bhattacharya, De Hoop, Katznelson, and Ullmann, which deal with problems like that. So you have sort of a layered medium, and you try to recover the various layers. So assuming that we have a foliation condition that is probably familiar to many people in this group. So we have a foliation condition with respect to the S and the P speed in the solid region, and we have a foliation condition with respect to the fluid speed inside the fluid. Then our theorem says that we can actually recover all three material parameters in the solid, and we can recover the wave speed in the fluid. So if G is Euclidean and we have two different systems for which the Neumann to Dirichlet map agrees, and we have additional assumptions for how the wave speed behaves at the interface, which is to guarantee that we don't have this total internal reflection forever that I mentioned earlier, then the wave speeds can be recovered in the outer manifold. The inner speed can be recovered in the inner manifold. And if a sort of technical condition is satisfied in the outer manifold, then you can recover the densities as well outside. So this, we have not said anything about whether you can recover the density in the fluid. I believe that this last paper I mentioned here is actually making quite some progress in doing that. This is non-trivial, but I haven't had a chance to read it yet. So I believe that it is possible that you might be able to actually do that. But okay, I am much out of time, so I'm going to stop here. If anybody is interested, I'd be happy to discuss more. So my last slide is here. Okay, thank you, and sorry for running over time.
Thank you very much, Nikolas, for the very nice talk. Thank you very much. Are there any questions or comments, please?
Hi, Nikolas. A very nice talk. I came in halfway through your talk. I had another meeting, so I apologize. Maybe my question is a dumb question, but are you solving Newtonian Navier-Stokes on the fluid side, like compressible Navier-Stokes?
No, so we're not using, let's see, actually, I have no idea how I can get to the early slides from this. Maybe there is a way to do that. So we are not considering a, okay, let me see. Okay, this is the way to do it. We're not considering a nonlinear equation in the fluid. So let's see. It is.
So is it Stokes? Is it some kind of Stokes model?
It is the system, the pressure velocity system.
I see. Okay.
So this
in inviscid fluid. Oh, I see.
Yeah. So we're not assuming viscosity.
Okay, but I mean, okay. So then you have issues of. Oh, but it's linear. Okay, never mind.
It's
okay,
linear,
so
yeah.
okay, so this is what post. Okay, I see.
So,
okay.
So it is. At least I didn't think it was easy to to show well-posedness because so in this let's see, so the way we showed well-posedness is let's see, let me go a little bit below. I don't know if you were.
No, I don't mean well-posedness of the coupled system. That's tricky because of the boundary conditions. And no, I meant just the fluids by itself. If you were
okay, yeah.
Just the fluids, okay. And then, so, and have you thought of, okay, maybe in this linear system it becomes trivial, okay, but have you thought of a incompressible limit?
So you mean taking the limit as mu goes to 0, basically?
Yeah.
Yeah, okay, so this is actually a very good question. I should have mentioned that. So the thing is that I should have mentioned that this operator here, so the way we showed well-posedness, I mean, we sort of decoupled this pressure velocity system, and we wrote one for the displacement. So this operator is basically the same as an elastic operator, but with mu equals 0. But the point is that you lose the ellipticity, and because you lose the ellipticity, I don't know, all sorts of bad things happen. And so, I mean, so for instance, in the Stefano Fulman and Vashi paper that I mentioned, they're dealing with two solids being in contact case. So, in principle, you could see what happens if you try to send the mu to 0, but it's not clear that it should work. I mean, you have to show ellipticity of all those, matrix to the differential operators, and then suddenly you get such a big kernel on that. So, I think you have to rewrite it into using potentials or. But yeah, that's a good question, though. I should have mentioned that. Thank you.
Thank you. Very nice talk.
Thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Nikolas, could you please say a few words about the idea of the proof, I mean, of your inverse result? You have probably some slides.
Yeah, okay, so so this was, I have some slides about it. So the idea is very similar to what was done in the Stefano Fulman and Vashi paper, which again builds up on previous work by a number of previous authors. So first of all, the recovery of all materials in the outer layer, this is basically, we're completely quoting it. I mean, the situation is completely the same, So in what they're doing, they have here they would have a solid and another solid below. But how you recover the materials in the solid, it doesn't actually interfere with what you have in the sort of second layer. So that one, I believe the way it goes is you have to recover you can recover the scattering relation, I believe, and then from the boundary rigidity result of the same authors, you can recover the wave speeds. And once you have the wave speeds, then the works of Rachel and the one that I mentioned by Bhattacharya, which is sort of adapting those ideas to the partial data situation, you can also recover the density in the solid, because you have those three parameters that you want to recover, and generally the density is more difficult to get to. So that's how you get the first layer. And for the second layer, we basically just recover the travel time between points with respect to the first speed. So let's see. So you choose 2 points here, and you look at the sort of CF, C square F, G. Well, G is Euclidean. Well, the geodesic which connects the two, and you construct a solution that's is sort of microlocally supported along the corresponding bicharacteristic and so on. And then you construct a full solution by basically propagating back into the outer layer and killing off any reflections. And actually for that, this is where this control comes in that I mentioned earlier, that whatever wave you want to have in the fluid, you can produce it by sending suitable waves from the solid. And so then you can do that, and that gives you some sort of Cauchy data in the outer hypersurface. And let's see, so yeah, you get some data on the outer hypersurface. You construct corresponding solution with the second, the tilted, let's say, system, and then you know that your media are the same out here. You have already recovered the position of the interface, and that allows you to say that you can, for the solution of the tilted system, actually, you're going to hit this point X, and by time reversal, you're actually going to hit that point Y, and you're going to do that in the same amount of time, and you recover the travel time. And once you have the travel time, then the boundary rigidity result of Stefanov, Rubin, and Vashi gives you the wave speed. I mean, it's essentially the same idea that was used in the like more recent SUV paper, the 21. It's just that there, I believe they're recovering the scattering relation in this boundary, whereas we're just using the travel time, it's kind of easier in some sense.
Yeah. Thank you very much. Thank you very much. Are there any other questions or comments, please? Any other questions or comments? If not, thank you very much, Nikolas, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Thank you.